Hello and welcome to Science with Dr. J. This is our episode number 3, Meet the Characters. And as I promised you, we will start from the beginning, from the Big Bang, from when the universe first started, 13.8 billion years ago. So what's this Meet the Characters? What is this about? Well, in order to appreciate and understand the Big Bang theory and what happened at the time of the Big Bang and afterwards, there are certain things, we have to deviate a little bit. There are certain things or phenomena that you have to understand and appreciate, and this will help you understand better the Big Bang and other things in the coming episodes. So Meet the Characters is just going to help us understanding some phenomena in nature that are important. So here we go. These are the characters. Measurements, scientific notation, atoms, light, the Doppler effect, energy, 4 basic forces of nature, gravity. That probably means nothing to you now, but I hope in the next half hour I will help you go through all that and understand it, because understanding those will help you understand many other things that we will discuss in the episodes. Now, I hope it will not be boring. I'll try to make it as interesting and as easy as possible for you. So bear with me, and I think we'll come to a good understanding of these phenomena. First, measurement. When we measure things, what do we measure exactly? What things do we measure? There are 3 basic measurements in physics that we use, and when we use those 3 basic measurements, they help us understand or derive many other measurements. The 3 most basic measurements that we rely on in physics are time, and we measure time in seconds, and mass, we measure mass in kilograms, and distance, and we use meter as the basic unit of measuring distance. Okay, so seconds for time, kilograms for mass, and meters for distance. Those are 3 basic measurements. And you know, it's amazing, because out of those 3 basic measurements, we can come up or derive many other measurements, as you will see now. There is one other measurement that's very important, and that's temperature. Temperature is used to be measured in Fahrenheit in the old days, but in science we rely on Celsius or on Kelvin. And 0 degrees Celsius is equivalent to 32 degrees Fahrenheit, and it's equivalent to 273.15 degrees Kelvin. These are the basic measurements of temperature that we use. So, all right, let's look at the parts that are smaller than a meter and parts that are larger than a meter. So a meter can be divided into centimeters, millimeters, micrometers, nanometers, okay, and we can go as small as an angstrom, which is 1/10 of a nanometer. That's smaller than a meter. Bigger than a meter, then we have kilometer, and then beyond kilometer we come up with another unit. It's called the astronomical unit. What is that? What's an astronomical unit? The astronomical unit is the distance from Earth to the Sun. The distance from here to the Sun is 150 million kilometers. Okay? So that's in order to help us appreciate distances in space, which are huge, as you will see in the coming episodes. We use the astronomical unit as a guide. The distance of 150 million kilometers is the distance from here, from Earth to the Sun. We call that astronomical unit. What's bigger than that? Bigger than that is a light year. Light year is something that I will show you shortly, so I'll not say anything about it now. And bigger than that is a parsec, which I will also explain to you a little bit later. Okay, so that's distance. All right, well, how about mass? Kilograms. What's less than a kilo? A kilogram is made of 1,000 grams, and each gram is made of 1,000 milligrams, and each milligram is made of 1,000 micrograms, and each microgram is made of 1,000 picograms. So these are the parts of mass that are smaller than a kilogram. But the basic unit that is used in physics, in science, is the kilogram, actually. So what's bigger than a kilogram? Well, we go by thousands. So there is a ton, a metric ton, we call it, which is 1,000 kilograms. Or there's a kiloton, which is 1,000 tons, or 1,000,000 kilograms. Or a megaton, which is 1,000 kilotons, or 1,000,000,000 kilograms. So these are the mass measurements that we use, but the kilogram is the basic unit that is used in scientific, in physics in particular, to measure the different parameters in the world of physics. And then we have the second to measure time. So what's smaller than a second? The second is divided into milliseconds, 1,000 milliseconds. Each millisecond is divided into 1,000 parts called microseconds, and so on. And what's bigger than a second? Well, 60 seconds is 1 minute, 60 minutes is 1 hour, and 24 hours is a day, 365 days and 6 hours is a year, and so on. So these are the basic measurements that we use for time and for mass and for distance. So you should be familiar with them. And they'll become second nature as you deal with them in the future. If you go into a science career, they'll become second nature, and it'll be easy for you to understand them and use them. There are other units, actually, that we should look at, and not just the temperature, which is Kelvin, and the distance, which is in meters. And there's another unit that I didn't tell you about. It's the ampere. The ampere is the unit of measurement for electricity. We call it the ampere, abbreviated capital A. And, of course, we spoke about the second. But there's another one called the mole. In chemistry, it's very important to speak about the mole. What is the mole? The mole, it just refers to the amount of substance. The amount of substance in a certain number of molecules or atoms. And we'll talk about that later in detail. The kilogram we have already discussed. And then there's the candela. The candela is the unit of measurement for luminosity. How luminous a certain source of light is. We use the candela. So, and if you notice at the top here, it says International System of Units. All scientists all over the world agree to use the same units so that they can be speaking the same language. And so it's called the International System of Units, and it's abbreviated SI. Why is it called SI? Because it was originally agreed to and formulated in France, and so SI stands for two French words, Système International, which means international system. Okay? So these are the units of measurement in science. Here's a very interesting one that you should be familiar with, perhaps, or you heard of it, but it's called the pi. And the value is 3.1459, so many digits, and it doesn't finish. Those digits can go indefinitely. You can just keep, you try it yourself. You divide the number 22 by 7, and you do it manually, and you see, you go through thousands and millions of digits, and it will not finish. What is pi? Where does it come from? You know, this is really amazing, actually. If you take any circle in the world, it has a center, and it has a perimeter, right? The whole distance, the whole perimeter is called circumference. If you take any point from the perimeter of the circle and draw a line from that point to the center of the circle, that's called the radius. And if you continue drawing the line from the center to the opposite side, the same line continues to reach the other side of the circle, The whole distance is called diameter. So a diameter of a circle is twice the radius. Okay? And the radius is the distance from the perimeter to the center of the circle. Now here's what's amazing. If you take any circle, even a very tiny circle that you can't even see with your own eyes, or a circle as big as the whole solar system or the whole galaxy, or as a circle as big as the whole universe, it doesn't matter. All circles have one amazing single property. And what is that? If you divide the circumference of the circle, okay, by the diameter of the circle, which is 2 radiuses, you get the same number. If the circle is this small, or if the circle is big as Earth, or as big as the solar system, or as big as the whole universe, it doesn't matter. Every circle, no matter how small or how large, has the same value if you divide the circumference by the diameter, and we call that pi. Okay, and we abbreviate it with the Greek letter pi. You will notice that in science we use a lot Greek letters. And we'll cover that in coming episodes, so you'll be familiar with a lot of the Greek alphabet, both the capital letters and the small letters. This is a small letter pi, or the letter P in Greek. It's abbreviated in this shape that you can see where it says pi. So, that's the symbol of pi. You should be familiar with that because we'll use it in the future. So, how do you use the different units to come up with other things in physics? For example, we speak about speed. Okay? The car is speeding or going really, really fast. What does that mean in physics? It means how much distance it's covering per unit time. Unit time, as we agreed, is a second. We use seconds in science. So how many meters is it going in a second? That's the speed. So if you take the number of meters, divide them by the number of seconds, you get the speed. Another expression that is used in physics is called velocity. There's a slight difference. It doesn't concern us now. We'll learn about that later on in other episodes. But speed, velocity, for all practical purposes, for our purposes now, it's the same. All right, so that's speed dividing distance by time. So, what's next? We spoke about velocity or speed. Now, if you go from one point to another point at a constant speed, okay, so you cover a certain distance. But if every second as you go, you increase your speed or you increase your velocity, then this is called acceleration. And look at this figure of a girl running. At the top you can see she's running at constant speed. So she's covering 10, let's say 10 meter distance. But if she increases her speed, after 1 second, she goes double the speed. After another second, she goes 3 times as fast. After another second, she goes 4 times as fast as when she started. And then she goes 5 times as fast as when she started. She's accelerating. We call that in physics acceleration. She's increasing her speed. Her speed is going up with time. So if you take her speed or velocity and divide it by time, that gives you acceleration. And we abbreviate it in physics with the small letter a. So that's what acceleration is. It's a change in speed over time. So look at this interesting thing that we can use. Now that we have learned about distance and about acceleration and about speed, we can use that information to come up with interesting things. For example, okay, look at these two animals. They're hitting each other very, very strongly using their horns. And so there's a force. This animal is using force, and this animal is using force to hit the other animal. What is force? In physics, force is multiplying the mass times the acceleration. You already know what acceleration is now, because it is the speed changing with time, and mass is just, measured in kilograms. So if you multiply the mass by the acceleration, that's how you measure force. You see, using the three basic units, which are mass, distance, and time, we can calculate force. Okay? Here's another example. When you go sometimes drive around in some places or in some cities, they have signs to warn you about animals that cross the road. So they ask you to reduce your speed down to very low speed, because if you hit the animal at very high speed, then the animal can actually harm you. The impact will push the animal against the glass, the windshield of your car, and it will shatter and it will cause serious damage. In fact, a lot of people die if they hit an animal at a high speed. That's why you should lower your speed when you drive where there are animals are crossing. And if you take the mass and multiply it by speed, you get what we call momentum. Your momentum is very, very large if you're very heavy and going at 10 kilometers a second. Okay? But if your mass is small, maybe is only 1 gram, going at the speed of 10 kilometers a second, you have some momentum, but it's not as serious as if you have 10 kilograms going at the speed of 10 kilometers per second. So momentum is very important in physics, and now you understand it. It's still, as you can see, using units of mass and distance and time, just those three things, to come up with momentum and force and acceleration and speed and all the other variables in physics. Here's another one, energy. See this little boy, he's pushing the car. His muscles have some energy, but not very much. But strong enough to move a toy truck. He can give it a little push, and energy from his muscle comes and pushes the toy truck, and it's moving. Okay? If he uses the same amount of energy from his muscles to push a real monster truck, will he be able to move it? No, it will not even budge. Why is that? There isn't enough energy because the big real monster truck is huge mass. So the amount of energy needed to move it is much, much higher. So how do you move? How do you calculate the amount of energy? You multiply the mass you multiply half of the mass by the speed twice. You multiply by the speed, you multiply by the speed again. And this is measured in joules. Okay, we call the unit of energy joule, Joule. Okay, so that is the unit of measurement for energy. But it comes from mass, and from distance, and from time, as you can see. So all of the units in physics derive from these three basic units. Okay, how about pressure? You've heard of pressure, this big pressure and small pressure. What does it mean? If you take a certain amount of force, okay, which we have already defined, you understand what force is, right? It's the mass times the acceleration. That's called force. So if you take that force and divide it over a certain area, say 5 square meters, then there's a lot of pressure, because each meter has 1/5 of that force falling on it. But if you take that same force and you put it over an area that is a lot bigger than 5 meters, double, 10 square meters, then that same force is distributed among 10 square meters instead of 5. So therefore it will be half of the pressure that you get when you have that same force over an area of 5 square meters. So pressure is the amount of force against a certain unit area. That's what pressure is. Again, as you can see, we're using distance, mass, and time to measure pressure. Okay. How about density? You've heard of density. This is dense, this is not dense. So if you take sponge, about this big, 10 centimeters by 10 centimeters sponge, a cube of sponge, and you have a cube of iron, okay, which one is heavier? Iron, of course. So if you put them on a seesaw, the iron will go down immediately. Why is that? We say because iron is more dense. What does density mean? How much mass there is in unit volume. So in this 1,000 cubic centimeter box, you have a huge amount of mass from iron compared with a smaller amount of mass with a sponge, because most of the space is air. In a sponge, most of the space is air. There's very little material. So it's not as dense. So density is how much mass in unit volume. Okay. But in science in general, we use very, very small numbers and we use very, very large numbers. When you start writing zeros, it becomes really complicated to write all the zeros. So let me show you an example. Look at the blue chart on the left here. Well, you start with 1. 1 is easy. 10 is easy. 100, okay. 1,000 is 3 zeros. 10,000, 4 zeros. 100,000 is 5 zeros. And then it gets to be complicated and hard to read. When you have 6 zeros and 10 zeros and 15 zeros, it becomes extremely difficult to write down. So that's where scientists came up with what we call the scientific notation. The scientific notation is you just calculate the number of zeros and you write the number 10 and you write the number of zeros as a superscript. Okay? That means a smaller number above the number 10. We call it superscript. Or in science, we just call it 10 to the power 2 or 10 to the power 8 or 10 to the power 10. That's how we express it. And that's an easier way to write large numbers. So if you write 10 to the power 3, that means 1,000, because it's 1 with 3 zeros following it. And the same with, so if you go 10 to the power 8, that means 100 million. That means 1 with 8 zeros following it. So if you write 10 to the power 8, suppose you want to multiply 10 to the power 8 times 10 to the power 7. That means 10 million times 100 million. What's the answer? Instead of writing all these zeros, you just add the 8 and the 7, and the answer is very simple. 10 to the power 15. And that's it. So now, this is the blue chart. Look at the orange chart here on the right. Well, with this chart, then we deal with small numbers. So the decimals. So if you go 1 and then 0.1, 0, 0, 0.01, and then 0.001, 0.0001, it really becomes difficult to write that. So an easier way is we do it exactly the same. We raise it to the power, but instead of writing the power 1 or 2 or 3, we make it to the power minus 1, minus 2, minus 3. So if you write 10 to the power minus 3, what does that mean? It means 1,000 or 0.001. Okay, because you have 3 decimals to the right of the decimal point. So that's how you write. That's what we call the scientific notation, and that's how you write numbers in science, because you're dealing with the very small and with the very big, and that's the only practical way of dealing with them. Okay. So, for example, if you go, there's something called orders of magnitude. You should be familiar with this term. So if we say 100 is one order of magnitude bigger than 10. That means it's 10 times bigger. If you say 1,000 is 2 orders of magnitude bigger than 10, that means it's 100 times bigger than 10. Okay, and so on. All right. Now we talk about atoms. Everything is made of atoms. Every single thing around you is made of atoms. Your body is made of atoms. And these 2 kids in the field, the clothes they're wearing is made of atoms, the trees are made of atoms, the soil, the flowers, the cameras, the stand for the camera, the sky, everything around them, every substance around them, at the basic level, when you break it down, the basic unit that builds all elements in nature is the atom. And what is an atom made of? Well, okay, atoms are made of positively charged positive electric charge proton, okay, surrounded with an orbit around it, an electron that is negatively charged. That is the simplest atom, hydrogen. Very simple. There's a proton with a positive charge, and there's an electron orbiting around it with a negative charge. It's not actually like that. This is a very simple illustration, of course. We will talk later on in other episodes about how it really is. I mean, the electron is not just a particle whizzing around the proton. It's a bit different than that. It's more like a wave. But we will speak about that later. But for now, it's okay. Hydrogen is the simplest atom. One proton, one electron. So I will ask you a question. What is the charge of an atom? 0. Because positive and negative attract each other, and they cancel each other out. So the net charge of an atom is always neutral, 0. So atoms have a neutral charge because they have an equal number of electrons and protons. Okay? All right, so what's more complicated than hydrogen? Well, the next element after hydrogen, the next element after hydrogen is helium. Helium is interesting. It has a new kind of particle. Helium has 2 protons and 2 electrons. So obviously it is neutral. It's not positive or it's not negative because the 2 protons are positively charged. The 2 electrons are negatively charged, and they cancel each other out. So the atom is neutral. But there's something new here, something interesting. The helium also, in the nucleus, we call the central part of the atom the nucleus, has 2 neutrons. What's a neutron? It's a particle that is equal to the proton in mass, almost the same in mass, but it has no charge. So that's why you see this N here for neutron is written N with 0, which means it has no charge. Okay? Well, so that makes the helium atom 4 times more heavy than the hydrogen atom. Because the hydrogen atom has only 1 proton, and the helium atom has 2 protons and 2 neutrons of almost the same weight, mass, and so the total mass of the helium atom is actually 4 times that of the hydrogen atom. Okay, that's good. Let's look at some interesting things here. If you remember, I told you positive and negative, things that are positive and negative attract each other. But 2 negative electrons will repel each other. They go away from each other. Like in a magnet. If you have the south pole and the south pole of a magnet, try to bring them together, they will not. They resist. You need force to bring them together. And if you bring the south pole and the north pole of a magnet, they will attract each other. Okay? So attraction for opposite charges